Hello everyone, welcome to the week 4 now. We are coming to midway of this course. How is it going? How are you people doing? Are you people solving the assignments? See, even if you are not registered for examinations, you can solve your assignments and give it to us. We will tell you how you have done. It's also important that you people give us considerable feedback so that we can make some adjustments in the course. We are also going to supply you the solutions of the assignments. So, even if you do not submit these assignments to us, try to solve those assignments first and then look at the answers. Okay? So, that will of course help you. Right. So, we will start with the week 4 now. In the week 4, what I am going to do is, I am going to introduce the Hamilton's equations, and then from the Hamilton's equations, remember Hamilton's equations are defined over phase space, the idea which we learnt at the end of the last week. And then I will talk about symmetry principles and the conservation theorems, and finally some computational aspects like Ruthian procedure and so on. Okay. So, let us begin. As you are aware of the Fourier transform, you take a function, and when you take its Fourier transform, there is a information that is contained in the Fourier transform which is same as the original function, which also means that you can actually revive or get the original function again from the Fourier transform. And the Fourier transform is involutive. That means, if you take Fourier transform of a function twice, then you get the same function back. Legendre transform is also one such transform, and you actually have been introduced to Legendre transform in some context. I will come to that little later, and this of course is used in thermodynamics. So, I will give you one example from thermodynamics, but let us begin by the definition. Now, first I will describe or define what is called as a convex function. So, a convex function, so if you have a function which is defined over some interval of real line, okay, and it is a real function, we will call this function as a convex function. So, is convex if the second derivative of the function is greater than 0. Okay. In some books you will find strictly convex, which means the second derivative is strictly greater than 0, or in some books it is just called convex and is defined as when the second derivative is either greater than or equal to 0. What is the idea of this? Idea is very simple. The name suggests it is a convex function. So, the shape of the function is expected to be convex, okay, something like this. It maintain its shape over whatever interval over which. So, if the interval is given by a b, then whatever this interval I, the shape looks like a convex shape. As opposed to this, if the second derivative is less than 0, you get concave functions. Okay. Let me take one example. Suppose f of x is some a plus b x plus c x square, and where c is greater than 0. You can immediately see it is a parabola. So, it has this convex shape that we really want, and you can rigorously show this because the second derivative, which I will denote by f double prime at any x. Remember, this must be true for all x in the given interval I. So, f double prime x in this case is simply 2c, and because c was greater than 0, this is definitely 0 greater than 0 for all x. Okay. So, this is a convex function. Another example would be, take exponential function. So, e to the power x. What is the shape of e to the power x? So, shape of the e to the power x is something like this. It grows exponentially on the positive side, on the negative side it approaches 0. Okay. Now, second derivative of this is again e to the power x, and we already know that the exponential function is always positive. So, this is always positive and hence is a convex function. Now, if I take sine function as sine of x. Okay. Now, sine of x, remember if I plot this function from 0 to 2 pi, then sine function goes like this. Okay. So, you have 0 here, this is pi and this is 2 pi, and of course, beyond 2 pi also the function will rise again. Is this function convex? No, it is not. You can immediately see that its shape is in some parts like a concave shape and in some part it is like a convex shape. So, if I define the interval I, which is between pi to 2 pi, then the value of the sine function is negative. That is this section here, remember this section here. Now, if I take second derivative, this is minus of sine x, and this we know is definitely greater than or equal to 0 if x is in this interval between pi and 2 pi, and in fact, it is definitely concave between 0 and pi. Okay. So, remember the domain matters. A function may be convex in a domain, but it may not be convex in some other domain. Okay. Fine. And we will of course, here always assume that domains are connected domains, because in this case you have not just pi to 2 pi, but you also have 3 pi to 4 pi section where the function is again concave. So, when I am talking about functions here, we are talking about the functions on a connected domain. Okay. Now, what are the properties of this? The properties of convex functions are, first of all, that the f prime of x is monotonic function. In fact, monotonically increasing function for x in I. Okay. That is one property. The second property is, that property can you see very easily, because f double prime is always greater than 0. That means, change in f prime is always increasing change. Okay. So, this is very easy to see. How about this one? F has at most one minimum in I. Remember, the statement is very accurate. It is at most one minimum. That means, it may not have minimum at all, or it has one minimum. Okay. It cannot have two minima. Look at all these examples we have here. The first function, this is quadratic. This of course has one minimum, and that one minimum we can find by finding out f prime x. F prime x here will be equal to b plus 2c times x, which means at x is equal to minus b by 2c, you have a minimum. Okay. What about the exponential function? And this is of course the only minimum. Remember, it is a linear equation, it has only one solution. So, it has only one minimum. What about the exponential function? Exponential function does not have a minimum. Look at the shape of the exponential function here. It is convex, but it does not have a minimum. What about sine function? Sine function also, if you are looking at the single connected domain, which is domain between pi and 2 pi, then there is exactly one minimum, okay. And that of course has lies at 3 pi by 2 and it has a value of -1. Okay. So, this is the idea. Now, I will define the Legendre transform. Okay. Let us start with a function. So, a function which is defined over some interval okay, and we will assume that it is convex and also I will assume that it is smooth, that is it has sufficient derivatives, at least 2 derivatives do exist. Okay. Now, define a new variable which is s as f prime of x, and now think of this f prime as a transformation from x variable to s variable. Okay. And is it well defined? Yes, of course, because remember f prime is monotonic and because it is monotonic, its inverse exists, which means given s I can given x I can get s of course through this uniquely, and it is also invertible. So, I can also write x as f prime inverse evaluated at s. Okay. So, this is a one to one correspondence between x variable and s variable. Okay. Now, I will define the Legendre transform of f, and we will denote this by capital F. So, capital F of s, define it as s into x minus f of x. But remember, here capital F, which is Legendre transform of f, is a function of variable s. What about x? Remember, x is to be treated as, I will also denote this f prime inverse by some g of s. So, in a way x is a function of s. So, in this expression, if I want to write this very accurately, then I should write it as s into x, which is expressed in terms of s, minus f x again expressed in terms of s. And this is called as Legendre transform of the, and what is the domain of this function? So, the domain of this function f is clearly range of f prime of x. Okay, that is the map into s variable. Okay. Immediately look at examples. So, the first example that we had above is of the convex function is f was equal to a plus bx plus c times x square. Okay. Now, define the new variable s, which will be equal to f prime of x, which is nothing but b plus 2 times c x. This is invertible, invert this. So, after inversion you get x, which is equal to s minus b divided by 2c. And now, let us construct the Legendre transform. So, f as a function of s now is equal to s into x minus f of x, and this will be equal to s into s minus b divided by 2c minus, remember I have to write f of x not in terms of x, but in terms of s, which means this will be a minus b times s minus b by 2c minus c times s minus b squared by 2c squared. Okay. Simplify this, and if you simplify this, you get 1 over 4c times s minus b whole square minus a. Okay. It's a quadratic term minus the linear minus the constant. Okay. What is the domain of the Legendre transform capital F? That of course is again a real line. Now, let me take the second example. Here f of x is e to the power x. What is the derivative of this? That is again e to the power x. So, our new variable is s. Invert this. So, this immediately gives us x is equal to log of s. But now, what is the domain? Domain here is r plus, where s is greater than 0, okay? And the transform f of s is nothing but s into x. I will immediately substitute that as log s minus the function which is e to the power x, but e to the power x is nothing but s. Okay. So, that is done. And finally, the third example which we were looking at was the sine function, sine of x, then s must be equal to f prime x, which is nothing but cos of x, and we get x as cos inverse of s. And remember, the domain of the inverse function is minus 1 to plus 1. And the Legendre transform of the function small f is again x is nothing but cos inverse of s minus sine of cos inverse of s. Remember, this is the common mistake that students always do, which is they leave the Legendre transform in terms of the variable x rather than the variable x, okay? Or sometimes the mixed expression which contains both s and x, but that is not correct. Remember, you must always write the Legendre transform, which is, sorry, I made a mistake here, this is s. Always the expression for f must be in terms of the variable s. Wherever your s appears, x appears, that x must be replaced by the inverse transform, which is given here. Okay, that is done. Now, I will write down the properties. So, properties of Legendre transform. I will also use this notation. So, if you have given a function f, then transform is capital F. Okay. Now, the property number 1 is that capital F is also a convex function. Okay. Now, proof of this is very simple. Remember, f prime is nothing but df by ds. Remember, every time we take prime, we know the prime is taken, that is the derivative is taken with respect to its argument. So, in this case it is argument is this, and this df by ds is nothing but x, which is f prime inverse of S. So, let me prove that. So, we will start with f of s. This is nothing but x into s minus f of x. Okay. Then f prime is df by ds. Let us take this derivative. So, first of all, it is x. Let me write it on the next line. So, this is first of all, it is a product of x into s. So, it is x plus s times dx by ds and minus, remember, it is a derivative of f with respect to x. So, I will write it as df over dx into dx over ds. But notice that s is same as df over dx. So, these two terms will cancel with each other, leaving you with x, and this means that this is exactly equal to f prime inverse of s. Remember, this is the definition of the variable s. I will go back there, there it is. So, since s is equal to f prime x, x is inverse of the f prime equation. Okay. So, we have this. Now, to prove this, to prove that capital F is also convex, I need to take the second derivative of this. So, f double prime of s, which is nothing but derivative of f prime inverse, and that we already know how to take the derivative of inverse. This is exactly equal to 1 over f double prime x, but we know that the original function small f was convex. So, its second derivative is greater than 0, and hence f double prime for capital F is also greater than 0, proving you that f is a convex function. Convex function. Okay. Now, second property. Second property is that the Legendre transform is involutive, that is, it is its own inverse. So, if I take transform of f, which is f, then transform of capital F will be small f. Okay. This is what we want to prove. Okay. Now, let me assume, just to begin with, that this is to prove. Okay. Now, let the Legendre transform of capital F be denoted by capital G, and then we will show that capital G is actually nothing but the small f. Okay. So, G of some q, we will define it as. So, what does that mean? I need to define variable q, which is nothing but df by ds, and G of q is q times s minus capital F of S, which is in turn function of Q. Okay. Now, what I want to do is this. So, I define G of Q as Qs minus capital F, which is function of S, but in turn you have to write it as function of Q. Let us put this there. So, Q of S, but capital F is nothing but Q into S minus small f, okay, of Q. And then this immediately gives us this is equal to f of Q. So, thus G must be equal to f, and hence the inverse Legendre transform of capital F is small f again. Fine. Now, here is the property number 3, that is, if S is defined as df by dx, which I will write it as df is equal to S dx. Okay. Now, capital F is the Legendre transform of small f. So, variable x, remember while doing this earlier proof here, we have already shown that df by dx, this is nothing but, here is the proof, df by ds is also equal to x, which means x is equal to capital Df by ds, and this gives you d of capital F is nothing but x ds. And finally, remember there is at most one minimum in the function. So, f min, this is the minimum value of the function if it exists in the domain, and this we claim must be equal to minus capital F of 0. Okay. And similarly, f min is equal to, so because capital F is also a convex function, it also probably may have a minimum. Remember, it is only one minimum, but it may have, and that is in fact equal to minus of f 0. Okay. So, these are very simple properties. We can immediately see an example. Remember, the e to the power x function, this function is defined over the entire real line. So, this is a function defined over real line to r plus. Okay. Its Legendre transform is s log s minus s. Now, you look at the function s log x, this is defined over of course r plus, okay. And you can see the consequence of the property number 4 there. The Legendre transform of e to the power x has a domain which does not have a 0 in it, and that is why e to the power x does not have a minimum. But the opposite is not true. If you plot s log s minus s as a function of s, okay, so this is your capital F, which is s log s minus s, this function has a minimum and the function goes like this, and the minimum of this here, what is the value of that? Because exponential function is defined over entire R, f of 0 is defined, which is e to the power 0, that is equal to plus 1. So, what would be minimum of capital F, that is nothing but minus f of 0, that is minus 1, and you can show by simple calculation. We already know how to calculate minima. Calculate minimum of this capital F and show that it happens. So, log of 1, it will happen at s is equal to 1, log of 1 will be 0 and you get minus 1 as the value of the minimum. Okay? Fine. Now, an example from thermodynamics. In thermodynamics, you define the energy of the system. The energy of the system, typically the thermodynamic variables are V and S. This is the internal energy. Okay. It is a function of two variables, remember. Now, what I want to do is this. I want to transform only one of the two variables. I want to transform S. So, define T as dE by ds. Okay. So, here let me write down internal energy is function of V, of course, is volume and entropy. Okay. Define T as a new quantity as dE by ds and call it as temperature. Now, calculate the Legendre transform of E. So, Legendre transform of E, remember we are going to leave variable V as it is, that is volume, but only transform S. This I will denote it by letter H, and this is now function of V and the new variable T. Okay. This is called as Helmholtz free energy. Okay. And remember, mostly when we sort of look at this in the thermodynamics book, we are always interested in the differentials, we are not interested in the total quantities. So, remember dE typically is P dV plus TdS. Remember, P is a pressure. What is P? P, of course, it is a differential. So, P will be nothing but del E by del V, and T we have already defined as partial of E with respect to S. Okay. And what would be Helmholtz free energy differential? This, of course, will be P dV plus, look at what happens to the differentials there. There you go. So, according to this rule, this is nothing but S dt. This is how you use it. So, the thermodynamic potentials like internal energy, Helmholtz energy or Gibbs free energy, all these are Legendre transforms of the internal energy with respect to one variable or the other variable or even both the variables. Okay. So, let me also generalize this method to functions of many variables and probably simultaneously taking Legendre transform with respect to the arguments. So, the extension would be very simple. So, f is a function of two variables. Okay. Then you define new variables u as partial derivative with respect to x and v as partial derivative with respect to y. Remember, the convexity must hold. I will in a moment tell you what that convexity in this case would mean. Okay. Once I do this, I will define the Legendre transform of f, okay, which is function of variables u and v. I will denote it by a simple letter f function of u and v will be defined as x times u plus y times v minus f of x comma y. Okay. And remember, again x and y you have to write in terms of u and v. Okay. So, look at this example. So, let us say f of x, which is a x square plus 2 times b times x y and plus c times y square. Okay. Now, when I had one variable, I quickly defined the notion of convex functions. How will I define the notion of convex functions here? So, what you do is this. Remember, now of course, there are two variables there. There are two variables. So, when I take the partial derivatives of the second order, how many derivatives do I get? I get 4 of those. I will use a shortcut here. The partial derivative with respect to x, I will denote it as x. Okay. Then the second partial derivative is f x x. This is basically partial derivative, second partial derivative of f with respect to x. What would that be? That would be nothing but 2a. Then f y y will be equal to 2c. And then you can also take a cross partial derivative, which will be f of x y, which means take the derivative of the f first with respect to x, then with respect to y. Okay. And that will be 2 times b, and this is also equal to f of y x. So, order of the partial derivative will not matter as long as the partial derivatives themselves are continuous. Okay. So, now I have this. What I am going to do is construct what is called as a Hessian. Hessian is a 2 by 2 matrix where I put entries like this. Y y. Okay. This will be equal to, I have 2a, 2b, 2b and 2c, and the determinant of this Hessian, so let us call this as H, Hessian, this will be equal to 4 times AC minus B square. If this determinant is greater than 0, then we say that the function is convex function, and when this happens, then of course, you are guaranteed that the partial derivatives there, which we defined here, they of course, will be monotonic. See, the whole definition crucially depends on the transformed variable to be invertible. That means, you are going from x and y to u and v, and I must have a inverse transformation. So, if this is true, then you have a convex function. Now, this is only for 2 variables. What will happen if I have 3 variables? Then of course, your Hessian will become 3 by 3 matrix. Okay. If it is 3 by 3 matrix, wait, now there could be a complication. So, the correct way to define convex functions would be something like this. You take a Hessian, and the Hessian matrix, as you can immediately see here, must be symmetric, because the order of derivative does not matter, which means f of x y here is also equal to f of y. Now, if this is going to happen, then I have symmetric matrix. Can I find the eigenvalues of the symmetric matrix? Yes, and the eigenvalues of the symmetric matrix, all of them will be real. If they are real, then you look at each one of those eigenvalues, all eigenvalues of H must be greater than 0. Then the function is said to be convex. Okay. So, this is a rigorous definition of convexity. Okay. Now, we can calculate this. So, what is, so assuming that AC minus B square is greater than 0, then U will be equal to twice A x, remember it is a partial derivative of f with respect to x, plus twice B y, and V will be equal to twice B x plus 2 C y. And these are of course simultaneous equations in x and y. You can transform this back to x and y. So, you can get x which is equal to B u minus A v divided by 2 times B square minus A c, and y is, sorry, this is y, and x is equal to B u minus C v divided by 2 times B square minus A c. Okay. And then you write down the capital F. The capital F is function of u and v. This is nothing but u x plus v y minus f of x comma y. And this turns out to be, I will write down the final answer, which is 1/4 b square minus a c into minus c u square plus 2 times b u v minus a v square. There you go. Okay. So, this is how we take the Legendre transforms. Fine. Finally, one last example. In this example, I will take a function h which is function of p, which is given by square root of p square plus m square. And just a little bit of fun here. In a moment, we will recognize what this is. Now, this is a convex function. So, let me define a new variable beta, which is derivative of h with respect to p, and that we immediately can write down as p divided by square root of p square plus m square. And now, you write down the Legendre transform of H. So, Legendre transform of H will be equal to p times beta minus H beta, and simplify this. Once you simplify this, you get minus m times square root of 1 minus beta square. Do you recognize what this is? This is, in fact, I will denote it as L as a function of beta. This is in fact the Lagrangian of a relativistic particle. That is the advantage of Lagrangian or Hamiltonian systems. You see, in case of Lagrangian, once I give you Lagrangian, it gives you through Lagrange Euler equations the equations of motion. Now, this is a procedure, you see, Lagrangian, two equations of motion. Now, when we went from Newtonian mechanics to relativistic mechanics, what happened? The laws of mechanics changed. And how do I get this new equations of motion? Remember, we redefined the momentum and then wrote down the equation as dp by dt as f. But that p now is not the old Newtonian p, but the new p. This equation of motion also can be obtained from some Lagrangian by simply using Lagrange's equations, and that Lagrangian just turns out to be this. Okay. So, here the Lagrangian for a relativistic particle is this, and then when you take its Legendre transform, you get Hamiltonian, but you recognize this too. What is this? This is total energy of the particle. That is it. So, this is how the Legendre transform gets used in physics. It of course appears in many places. We have seen one example of thermodynamics where it commonly comes. Okay. Now, let us apply this idea of Legendre transform to the Hamilton's equation of motion. We will start from a Lagrangian and define the Hamiltonian of the system as a Legendre transform of the Lagrangian, and then from there we will write down the equations of motion.